All right, so just like that, we're on the very last section of Unit 2, 2.4. We're going to look at errors in hypothesis testing. So in the last section, we learned about hypothesis testing, which is also called significance testing. So just like with anything, there in statistics, there is going to be errors from time to time. So we're going to talk about the different kinds of errors that we can make, the probability of getting those errors, how confident we can be in our tests based on those errors, as well as kind of what types of errors are maybe okay to have and maybe not okay to have. So remember, when we do a hypothesis test, we only have two conclusions we can get. We can either reject the null hypothesis, we can either reject the null hypothesis, or we can not reject the null hypothesis. Those are the only two conclusions that we can have. So if I reject the null hypothesis, meaning I say the null hypothesis is false, when really the null hypothesis is true, that means that I've made an error. If we call that a type 1 error. If I reject my null hypothesis, but my null hypothesis is actually true, then we have made a type 1 error. And the other way, if I don't reject my null hypothesis, and my null hypothesis is false, and I should have rejected it, then we have made a type 2 error. Okay, so we can use this table to kind of navigate this for a while until you get the hang of it. So in this first one, it says, H naught, there is no gender bias when allowing students to take AP courses. So if we were to do a hypothesis test for this H naught, it says first, describe what a type 1 and type 2 error for the situation would look like. Okay, let's start with type 1. Okay, so type 1 is we reject the null, but the null is true. Okay, this is our null in this case. There's no gender bias when allowing students to take an AP course. So we're going to do, yes, we reject it, but it is true. So we reject when H naught is true. So what does that look like in context? That would mean there is no gender bias when allowing students to take an AP course, but we would decide that there is. Okay, so again, the null hypothesis is that there is no gender bias. So a type 1 error, we would say this is false, there is gender bias. Okay, but an error would say that, well, actually, there is not. So what is the risk of this error in this case? What's the risk of making this conclusion falsely? So if we decide that there's no gender, if we decide there's gender bias, there is gender bias when taking an AP course, what are we going to do about that? What's the result going to be of making that conclusion? Well, if we decide there's gender bias occurring in a certain course, we're probably going to put certain protections in place to prevent that bias, right? And even though there isn't any bias actually occurring, that's not actually a bad thing to have in place anyways. It's not going to hurt anything to put extra protections in place. So the risk, I'll put bias protections put in place. But not needed. And I don't know, maybe for some reason that means that we end up spending money where we don't need to spend money. But I mean, again, it's not a protection that's bad to have. And honestly, as far as courses go, and yeah, like making sure that teachers don't have bias when grading your work, it's actually really easy for teachers to avoid being biased with you guys. Most of the time, what we do is we cover up your names, or we don't look at your names, or we have you write your names in the backs of your papers so that we don't see who you are until we've already got it completely graded and we're putting it in a computer. Very easy to avoid that bias. Anyways, that's not really relevant. Type 2 error. Type 2 error would be here, meaning we don't reject the null hypothesis, but we should have. So we fail to reject a false H naught. Okay. So that would mean that this is false. So there is gender bias. But we fail to recognize that. Okay, so what's the risk of that? That means gender bias is going unnoticed. So obviously the type 2 error here is going to be worse than a type 1 error. So when H naught is false, the likelihood that you'll reject it is called the power of the test. Remember, when we're doing a significance test, the whole point is we want to reject H naught. So the probability of correctly rejecting H naught is the power of the test. So that would be this part of our table here. So yes, we reject the null hypothesis, and the null hypothesis is false. This is correctly rejecting the null hypothesis. This is the power of the test. The probability of doing this is the power of the test, which sometimes we just refer to as the power. So given a decision or significance level, alpha, the probability that our significance test will reject a false null hypothesis correctly when a particular alternative value is true, this is our goal, is called the power of the test against the alternative. The power of the test is the probability against making a type 2 error. It's the probability that we don't make a type 2 error. So we have some formulas then that we can use to calculate, to find the probability of making these errors. So the probability of making a type 2 error we refer to as beta, got this little tail on the end. It's always equal to 1 minus the power of the test. The probability that we don't successfully reject the null. The probability of type 1 error is very simple, actually. We determine the probability of a type 1 error before we even start doing our significance test. It's alpha. We choose our alpha when we're doing our test. So I guess my thing here got put on another page. So we got one example here, and then we're done for the chapter. The professional school advertises that it can place an average of 35 graduates a week with sigma equal 6 and full-time jobs within 2 weeks of graduation. They decide to test this claim by determining the number of graduates placed each week for 10 weeks. They decide to conduct a test of a hypothesis, H naught being mu equals 35 against HA being mu does not equal 35, and to use a 0.05 significance level. What is the probability of a type 1 error? All right, so probability of a type 1 error is equal to alpha. Always, always, always. So what did they say alpha was? 0.05. So the probability of making a type 2 error is about 5%. So when we choose our significance level, and when we choose alpha, we are already determining the probability of us making that type 1 error. So you want to think about, what is the type 1 error? How bad is it if we make a type 1 error? Should we choose a 0.5 significance level? Or should we maybe be a little more conservative and choose a 0.01 significance level? So the type 1 error and the consequences of making a type 1 error is exactly what should drive you in determining what your significance level should be. I already said we pretty much always choose a 0.05 significance level. When we would want to choose a 0.01 significance level is when our type 1 error would have some bad consequences that we want to avoid. Okay? Moving on, part B, what is the rejection region? Rejection region, and that it says in parentheses here, that is for what values of X bar will the null hypothesis be rejected? Okay, so which values of X bar will be rejected? So let's see, part B. Since alpha is 0.05, the rejection region is the region outside of our 95% confidence interval. So if I had chosen alpha to be 0.01, then our rejection region would be the region outside of a 99% confidence interval. So to determine our rejection region, we have to determine the confidence interval. So I take my mean plus or minus my critical z star times the standard deviation, which for this one, the mean is 35. A 95% confidence interval, so we use the critical z-score 1.96. Standard deviation of our population is 6. Our sample size is 10. And so we end up with a confidence interval from 31.3 to 38.7. So that means if our X bar is within this interval, we would not reject our null. So the area where we would reject our null would be outside this. So it would be an X being less than 31.3 or X bar, or X bar is greater than our upper bound, 38.7. This is our rejection region. Okay, moving on, part C. It says, suppose in fact the average number of graduates per week is only 32. Find the probability of a type 2 error and the power of the test. So 32 here now is our alternative value. So to do this, we need to find the probability that our X bar is within our 95% confidence interval. Given our alternative value. Okay, so we can calculate that probability multiple ways. Let's just do it the easy way. We'll use normal CDF on our calculator. Lower bound upper bound, mean, sample mean, standard deviation. And that ends up being 0.64. So that means the probability of a type 2 error is 0.64. And the power of our test is the complement of that, 1 minus 0.64, which is 0.36. So that is a very high probability of making a type 2 error, so that's not good. And the power of our test is fairly low, so 36%. Okay, so we would obviously want our power to be very high, and we would want the probability of either of our errors, type 1 and type 2, to be very low. All right, so that's it for Unit 2. Let me know if you guys have questions, if I can help you on anything, if I can check your work. Don't hesitate to reach out, jump on a Zoom call. Let me know.